Okay, so welcome back to another video. So here we have a product of definite integrals, both with the same bounds from 0 to pi over 2, one with the integrand of the square root of sine of x multiplied with the integrand of 1 over the square root of sine of x, or inverse square root of sine of x in other words. This evaluation only just needs two functions. The first, well, there's really no order. The two functions being both the beta and the gamma function, and we're going to use its properties to evaluate this complicated integral. I wouldn't really say it's complicated because just from applying with those functions, everything is going to be so very simplistic that using those properties actually just comes down to just a simple answer. So you might be thinking, well, if it's just a product of integrals, isn't it possible that because they're under the same differential, we can just combine the integrands like products together with square root of sine of x and then multiply by 1 square root of sine of x, and then just from there evaluate it to see if we get the same answer just from applying to both gamma and beta function? To tell you the truth, I'm not sure myself if it's possible. I only say this just because when I tried solving this problem, that was not the first method that I went for. Instead, I was thinking that I know that sine of x, it could be written in a form of a sine slash cosine integral representation for the beta function. So that's actually one giveaway from this video. But I highly don't think that's possible. I know that there was a proof that, and I only looked at this from the indefinite integral perspective, where if you have two functions f of x and g of x, and of course that the antiderivatives that exists, that if you take the integral of f of x times g of x dx, it is possible to write as the integral of f of x ds multiplied by the integral of g of x dx. That's just me though. If you're telling me that it actually is possible to get to the exact answer that we will show here in this video, please let me know in the comments. So yeah, nothing else to add here, so let's actually just jump in. Okay, so here we have our following two functions. The first one we have is for beta of our two inputs x and y. And so we can write this in terms of a sine cosine integral representation. So that's written as 2 times the integral from 0 to pi over 2 sine, and then to the power 2x subtract 1, and I'll just call this input w, multiplied by cosine of 2 to the power 2y minus 1 of w dw. Okay, and then we can write this in terms of gamma functions, which just says that we can just write this as the gamma of x multiplied by gamma of y, and then divided by gamma of the sum of two inputs, x plus y. And now the next function, of course, gamma functions. So we're going to use that gamma of some real part s greater than 1 is equal to the integral 0 to infinity, and then of w to the power s subtract 1 of e to the negative w dw. We're going to use a well-known value that gamma of 1/2 is actually equal to the square root of pi, and I'm not really going to go over the computations of this. This is actually just pretty simple. It's straightforward from there. I'm sure anybody can do it. Another property of gamma function, we write this as gamma of s plus 1 is simply just equal to s multiplied by the gamma of s. So everything here we'll be using to rewrite our integral with using these following properties. So first we have our beta of x, our two inputs x, y. We use that integral representation over here, and then also with its gamma representation in terms of gamma functions. We use a gamma of s with the integral representation. Then we know that we have to use the well-known value that gamma of 1/2 is equal to square root of pi. And then here's another property that we'll also be using in terms of gamma as well to evaluate our product of integrals. So now let's actually write our each of our integrands in terms of this the representation over here. So let's first start off with the left integrand. So we have the integral from 0 to pi over 2 of the square root of sine of x, then dx. Now we just write this in terms of using this property over here, or definition, and we can write this as 1/2 and multiplied by 2 of our integral from 0 to pi over 2 of sine. Then we set the exponents equal to each other. So here 2x minus 1 square root, so that's 1/2. So set that equal to each other, find that input, and we get that this is just 2 times 3/4. Now subtract 1 of x, multiply with cosine of 2 times. So we have nothing for cosine of x in this integrand, so let's say that the exponent is equal to 0. So solve for that, set the exponents equal to each other from here. 2y minus 1 equals 0. Solve for y, so we have that in this case this is just 2 times 1/2, subtract 1 of x dx. Then from here we just write this in terms of our beta function, so this will be 1/2, then multiply by the beta. Here our input over here, the first input would be 3/4, then our second input would be 1/2. Okay, so that's our first conversion over here. So the left hand side equals this right hand side in terms of beta. Now next let's do the second integrand right here. So we just apply the same method as before. So 0 to pi over 2 of 1 divided by the square root of sine of x dx. So here we can write this as 1/2 multiplied by 2, then multiply by the integral 0 to pi over 2, then sine, set the exponents equal to each other, 1 over square root of sine of x. This is in other words, we can say this is the sine to the power negative 1/2 of x. So if we solve for the exponents, we have that this is just 2 times 1/4, subtract 1 of x, multiply with cosine. No cosine yet again, so it's just the same thing, solve for that, so it's just 2 times 1/2, then subtract 1 of x dx. Then if we just write this in terms of our beta function, we just write that this is just 1/2, then times beta of our first input, which would be 1/4, and then our second input being 1/2. All right, so now that's we solved for both conversions. So now we just substitute everything back into place. So here I'm just going to rewrite our same integral that we were given. So the integral 0 pi over 2 square root of sine of x dx, then multiply with the integral 0 pi over 2 1 divided by the square root of sine of x, then dx. Here we just replace everything back, so this is just 1/2 the beta of 3/4 1/2 multiply with 1/2 times the beta of 1/4 and then 1/2. Now simply from here we can just use our properties of gamma functions over here to rewrite everything with this the multiplication over here. So continuing forward, we have this as 1 to the 1 divided by 4, and then of course by using our properties of gamma, we have first the gamma of 3/4, then times gamma of 1/2, multiply with gamma of 1/4, and then multiply with gamma of 1/2, and then all this being divided by with the sums over here. So the first one we have is gamma of, right here would be, so 3/4 plus 1/2, that will be 5/4, and then our second input for the sum of gamma 1/4 plus 1/2, that's just 3/4. Further simplifying this out, we know that gamma of 1/2 equals square root of pi, so we have 2 of them right here. Multiply the 2 together, so the square roots just cancel, so it's just pi. So now we have pi divided by 4. The gamma of 3/4 cancels each other out, so now we're just left with gamma of 1/4 and then divided by gamma of 5/4. Now we're coming home stretch here. So the last part is we want to rewrite the gamma of 5/4 using this following property. So by doing so, we can see that, put it like this, we'll put this as gamma of 5/4 is simply just equal to gamma of 1 plus 1/4, where we can say that this is just 1/4 times gamma of 1/4. Then from here we can say that this is just pi multiplied by gamma of 1/4, then divided by 4, replaced with our rewritten gamma of 5/4 for here. Let's multiply with 1/4, then times gamma of 1/4. Then you'll notice that the gammas cancel each other out. We just put it like this. So this is also the next line here. So this is just canceled, this cancels, this cancels, this cancels, and therefore the final answer is that it's simply just equal to pi, a simple constant like so. And there we have it, the final answer in the orange box of our given like so. Nothing too difficult. It's simply just using, the properties of our two functions. I said only two functions are needed, and that's basically the gist of how we get everything from here. So yeah, that's pretty cool if you ask me.